Hi everyone, I'm Honhming, a PhD student at the JBCA, the Manchester University. Today I'm talking about transfer learning for radio galaxy classification. So in the talk, I will talk about why are we doing this project, and after that I will talk about the basics of CNN and also the transfer learning, basically convolutional network and transfer learning. Afterwards, I will talk about how we actually build a data set we use and train a model with randomly initialized weights. With the randomly initialized weights modeled, I will tell how we actually apply transfer learning using these models and how they perform, and finally it will be a summary page. Okay, so why are we doing this? So here's kind of a historic issue. Back in 1998, VLA actually already provide two catalog. One is MVSS, another is FIRST, both operated at 1.4 gigahertz. They're both radio continuum survey. Back then, for the first survey, the resolution is about 5 arcsecond, and the MVSS is about 45 arcsecond. The two surveys both have modest sample size, so no more than 2 million, and among them, the number that need visual inspection, so basically are well-resolved sources, are basically one order lower. But in the future, when ASCAP, MeerKAT, or even SKA come into use, we may have at least, like EMU survey done by ASCAP telescope, we will need at least 7 million sources waiting for visual inspection. So in other words, because when I was dealing with the MVSS data, I spent a year to actually build a catalog. If you're dealing with ASCAP data, you probably need 50 master students to do that for 1 or 2 years. So I don't think it's cost efficient. Another reason why we do this is it would be great if our current or archival knowledge, archival data can help when we do the future classification, because there are way more unlabeled data in the future, and it would be great if we now have a model and can be applied to the future. So that's why we do this. Okay, so now I'm talking about CNN. Here is an inaccurate definition I picked up from Wikipedia, but I'm not using that. I will talk about lemon and lime, basically. So the two fruits are both citrus fruit family. One is green, one is yellow. Surface slightly different, and the shape slightly different. For us human, when we saw an image of this, the image and these features will come to our visual cortex first and convolve with our knowledge in our mind. And finally, our brain would tell us, oh, this is a lemon or this is a lime. So computer can do the same thing, but you need thousands of images to train it. And afterwards, so basically it will extract features in here, transfer to knowledge, and finally result and basically gives you a classification. So that was a basic idea, a kind of a recap of convolutional network. Why I'm using this, because I need to explain what transfer learning will be used. So transfer learning, for short, basically means we use knowledge we learned from solving one issue to solve another issue, or help solving another issue. Maybe a different one, or maybe a similar one. So here, we can see these are kind of a realistic, high-resolution lemon images, and there is a pixel art images. We can just say this is a high resolution, that was low resolution. But so intuitively, I personally believe everyone here know realistic ones before they know pixel art ones. Maybe I was wrong, but yeah. Okay. But for machine, we are not sure which way will actually work, especially for the astronomical images. So what I do here is I wanted to test if knowledge learned from either side can benefit the other side. And that's why I use transfer learning. Okay, so now it comes to the next step, the real part. My data set is pretty much like the lemon-lime question. It's actually a binary class classification, which is a Fenerov-Riley class, which is a binary class widely used in morphology analysis of radio galaxies. So these things can be measured by what we call hotspot distance, HAS, to the largest angular size of a radial source. So the ratio, if larger than 0.5, we classify it as FR2. If not, FR1. So that was the basic idea, but in the real life, we can see here, images are not that classic, they varies a lot, and there are many subclasses of radial galaxy if we really look into that. So that's where we need transfer learning or CNN to come into play to actually do classification. Okay, so let's start with the CNN. So the structure of the network I use is pretty much like 2 pages ago, except I add another fully connected layer. So the structure are the same. For all models I mentioned here, I trained each model for the whole data with the whole training data set for 10 epochs. And epochs here means the times every image in the training set was imported. So here's the outcome. We try to evaluate our randomly initialized weight model using 4 metrics: accuracy, precision, recall, and F1 score. Basically, the larger these 4 metrics, and basically close to 1, the more complete and useful the model will be. And you can also, so these kind of been derived from a thing called confusion matrix and can be used to derive rock curve as well, as some of us actually mentioned today. So we can see here, which use the same strategy, every settings are the same, but we can see that if we train with the first images, the model will perform overwhelmingly better than the one trained with MVSS data. This is because first images have way more structural information of radial sources, and it has a better resolution and sensitivity. So that's our very first result, and actually for the first images we reached about 90.1% of accuracy of the general classification. So it's actually pretty good, but not that for the MVSS ones, and that's why we have transfer learning. Okay, so about the transfer learning, how do we use it? Here I provide you 3 strategies. Method 0 is actually to retrain the whole model using another data set. We are not freezing any layers. Method 8 and B are basically we have all the convolutional layers and pooling layer frozen and only training the fully connected layers. So that was the basic idea. Ideally, it will save your time if you use method A or B because you froze some layers. And here we go, we come to the result. Okay, so first things we care about is the time cost when we train model. Here basically is about the MVSS dataset training. If we can see here, if we use method A or B, actually we can save up to 79% of time, of training time. But if we use method 0, the time cost is slightly higher. But I will still keep the method because later I will show why I need this. Okay, so here is about the general performance. Actually, this is the validation accuracy, the learning curve here. So we can see that no matter we train on MVSS images or first images, no matter which method, which transfer learning method we applied, you will gain a kind of better starting point after the first epoch you're doing training. But better starting point doesn't mean you have a better final result when you finish the 10 epoch training. As we did here, method 0 could have a slightly improvement in the validation accuracy sense, but not the other 2. So that was the cost, because if you froze some layers, you actually slower the learning process. So, and I'm talking about the final point about transfer learning. Okay. So I mentioned about high to low and low to high strategy. What will they actually come to help or even make the things worse? So here's the thing. If we do low to high strategy, which means we focused on first image classification in the final sense, actually it drops dramatically and we have a kind of randomly guessed classifier. But if we do, sorry, I high to low. If we use high to low strategy, it's actually if we use method 0 to train the full data set and the full architecture, we can actually have about 1 to 2% of improvement, and which means it boosts model performance. And that's kind of a intuitive because you use way more information learned before and actually to boost a model you trained with way lower resolution and way less information number. So that's my very idea, and that's the very first result. So for summary, the first two are kind of easy to derive. We choose high to low for the current stage. We're not sure what will happen in the future if we test on other surveys like SUMS, like EMU of ASCAP, for instance. And choose which transfer learning method will be a trade-off. Depends on if you want to save your time or you want a better model performance. The third is kind of the most important thing I would like to talk about is, given that first images have 5 arcsecond resolution, and EMU survey for ASCAP will have 10 arcsecond in the future at best. If we use the strategy, it is possible that when learning the ASCAP data, it will be boosted. However, the other next generation radio telescopes, especially like SKA, will have way, way better sensitivity and resolution. So this can be an issue. We might need other method, or we might need other path to actually solve this in the future. And the deadline is coming, so we might need to hurry up. So thank you guys, and questions?
Still full from lunch. Second call. Yes.
So have you actually looked at the initial CNN layers and looked at some of the kind of feature extraction perhaps between the pre-trained and the not trained one?
I'm sorry?
Have you looked at the actual features in the kind of pre-trained model and then in the transfer learning one to see what the differences are?
Basically, I haven't done the direct comparison. I did plot them, but I didn't do the direct comparison, and I will do that later on.